Okay, I think that Uwe, can you still hear us? Uwe? Just give me 1 second. A weird problem here. We're getting there.
We don't need that one?
It's on.
Oh, it's on. Okay.
Yeah, it's green, so it's on.
All right.
Is it on this?
Yeah, it's on. Apparently,
Just leave it there. It's connected. Yeah.
It's wireless.
Uwe, can you still hear us? We don't see you anymore. That's not good.
That was very clever here.
Uwe.
I thought it was lying around here, but actually.
Well, now everything is connected, but we lost the speaker. That's not good. Let's see.
Yeah. I need to see, but I want to see the chat.
Uwe, are you here?
Yeah.
Okay, we don't see you anymore.
Yeah, I will put it on. Yeah.
Okay. So this is just to say we are already on YouTube. So this is live stream before I went to plan. And we are, sorry for the slight delay. We are now ready. And I just wanted to announce briefly a technical thing. So this first part of the event is one separate meeting, which will be shared via one YouTube live stream and Zoom meeting. And then for technical reasons, we will switch off briefly for in between and switch over to another Zoom meeting. Yes. And if you wanted to also attend the second talk online, please make sure you have the other registration as well. You just go to the GReTA webpage for the second talk and get the link if you haven't done so. And so I would like to pass the word briefly to, well, we have two hosts, of course, François Metayer for the higher categories work group. And also Reiko Heckel.
Hello, Reiko.
I hope so. And I'll try to put the camera to the two hosts if there are interventions. And yes, Uwe, thank you very much for being here. Thank you everyone from both the work group and from GReTA to attend. And without further ado, I will pass over to you, Uwe, for the talk. Thank you.
Okay, thank you. I tried to do my best, and as usual, it was until the last end, but at least I managed to produce something, and I'm very happy to be asked to give a talk, and let's see how it goes. So in this talk, I tried to explain or show a little bit that there is some category theory and some mathematics behind the whole stuff, and so I mean, some people know me, but just short. So I'm from the former East Germany. I made my PhD in '88 on the theory of partial algebraic specifications. So I became a specialist in partial algebras at that time. And my supervisor was Horst Reichel. And 1 year later, it happened something. And I went to the Technical University Berlin after the wall came down and did a lot of stuff over the years, categorical algebra, abstract model theory in the sense of institutions and similar things. graph transformations by accident because I was in Hartmut's group, coalgebras and generalized sketches as a foundation of model-driven software engineering. And I have to warn you, I'm not a category theorist. I just learned category theory by need. And I'm a kind of dinosaur if it comes to technology and especially to presentations and diagram drawing. So I apologize for possible flaws concerning category theory and rather unsophisticated presentations. I never took time to learn this, really. I'm sorry. Good. When we started, so the idea was I went in 2000, I moved to Bergen, and after a while I said, no, I cannot just do theory. I have to make something applied. And I remembered about these things Norway did, and Alfio Martini showed me the time in Berlin. So, and, and then we looked at this, and model-driven software engineering became an own topic at that time. And so our approach was a software model can be described as a generalized sketch for an appropriate category of graph-based structures. So by graph-based structures, we mean in the broader sense pre-sheaves or corresponding slice categories, and an appropriate signature characteristic for the type of software model we try to formalize or to work with. And the origin of generalized sketches. So I know about Norway because I looked at this when I still was in Berlin. But later I also realized that he and Makkai developed generalized sketches in parallel in the 90s. And Makkai's approach to generalized sketches was motivated by an abstract formulation of completeness theorems and logic, while the group in Latvia had some industrial cooperation, and they have been very much concerned about data modeling and the foundation of data modeling. So, and as I told, so it's now 17 years ago, we kind of relaunched this generalized sketch approach of Norway. And we started to further develop it as a theoretical foundation of model-driven software engineering. Then our PhD students came back from conferences and said, no, we have to change the name. We cannot call it generalized sketch. They don't believe that it's correct, that it's precise. So we had a long discussion about it and called it after a while diagram predicate framework. And we also don't use in these papers and this work the term sketch or generalized sketch. We just call it diagrammatic specification. So what I will try to do in this talk, I will focus on Makkai's work, touch upon its application in homotopy type theory, and I will outline some recent extensions of this approach. And the Norway's approach I will rather talk about in the second talk. And you can just ask things in between if I'm too fast or if you don't understand things. So this is a paper, the first one. So I read already the corresponding technical reports, and that's this paper of Makkai, Generalized Sketches as a framework for completeness theorems. And later, this was around 3 years ago, I got a new colleague, Håkon Gulterud, and he is doing homotopy type theory. And it turned out that he's also very much fan of Makkai, but of this other paper, first order logic with dependent sorts. They call it the Folds paper. And this paper is never been published. But yeah, so I looked also at this paper, and I will try to talk a bit about these two papers. Yeah, and here I wrote that I struggled many years with the first paper and never came completely through. Yeah, it's true. It's just very, very compact notation and very, yeah. But I managed kind of. So, and my talk, what the things I present or how I present is coming from this lately paper I wrote. where I try to outline an abstract framework providing a unifying view to a broader spectrum of specification formalisms like algebraic specifications, horn clause logic, first order logic, Ehresmann sketches, generalized sketches, description logics, and things like this. So that's a very thing, and I will talk, especially also in the second talk, a little bit more about this paper. Good. So categories, there are very, very different definitions, but the definition or the point of view that is most appropriate if it comes to sketches and generalized sketches is to see a graph. A category is a graph where we have in addition identity loops and composition satisfying the identity and the associativity law. So, and in the 60s, Charles Ehresmann invented a graph-based specification formalism, the so-called sketches. Later, sketches were promoted for applications in computer science by Wells and have been also applied to data modeling problems by Johnson Rosebrook. They actually started to make a tool for database design based on sketches. That's a definition of a sketch. It's a very, very simple thing. We have a graph. We have a set of diagrams in this graph, a set of cones, and a set of cone cones in G. Yeah, that's all. So that's a sketch. And so sketches can serve. So in the first approach, one can say, okay, we have sketches. We will use sketches to formalize our software models, for example. So it can actually serve as a diagrammatic specification formalism, especially in mathematics. And the model of a sketch, I don't know if this is the original definition from Ehresmann, but this is at least in Bauwels. So what is a model? We have a category. Then we have a graph homomorphisms from the underlying graph of the sketch, G, to the underlying graph of the category C, such that each diagram in D is taken to a commutative diagram. Every cone in L is taken to a limit cone, and every co-cone in K is taken to a co-limit cone, respectively. So I'm coming from algebraic specifications, and I want to mention this. Many sorted algebraic specifications with equations can be transformed into equivalent finite product sketches. And if you want to use also conditional equations, then you end up with finite limit sketches, because you have to solve equations and describe inclusions of sets of solutions of equations, and so you come to finite limit sketches. That's just the side remark. We can, for example, define a finite limit sketch specifying the concept category, and the model of such a sketch in a category C is usually called an internal category. So another, I don't see the headlines here. Another way to perceive sketches, or another role sketches can play, is that in analogy to the representation of groups by sets of generators and sets of defining relations, we can utilize sketches as representations of categories. Yeah. So a sketch S represents a category if C can be in one or another way characterized as a category freely generated by S. So, for example, syntactic Laurier theories for our finite product categories freely generated by those finite product sketches that corresponds to many sorted algebraic specifications with equations. So this is my approach, or how I learned these, what sketches are good for. So I will not discuss now. I will discuss it in the other talk, why general sketches are not so useful in software engineering, or not yeah, not good enough or not appropriate enough. So, and here I will just go to the points. So there are two dimensions of generalizations. So we gave up the restriction to commutative limit or co-limit properties respectively, and we just allow arbitrary properties, arbitrary predicates. And then we are allowed to choose any category that is suited us instead of the category of graphs. And if we go for such a general approach, we need some formal overhead. And the first is we have to introduce names for our properties, for our predicates. So we had a lot of discussions and misperceptions of our papers, DPF papers, because we used always the term signature. Therefore, I decided now to use the term footprint instead. So what do I mean by a footprint? We have a, yeah, and I use the name feature instead of predicate, just to have something that is not used also to point out that things are a little bit more general here. So we have feature symbols or predicate symbols, and each of these predicates has a certain arity, and this arity is just an object in this base category. Yeah, in the category of graphs, it will be usually a finite graph, and this is called the arity of the feature symbol. And here's just an example. Yeah, if we want to start to reconstruct the concept of category by means of generalized sketches, then we start with the category of graphs. Then we have a predicate that tells us that a triangle is a composition. Yeah, that xe3 is a composition of xe1 and xe2. And we have a predicate that we can put. That's a statement, a predicate on loops, that this loop is the identity. So there are still not yet footprint operations and footprints. We are working on. That's an example from one of my PhD students from Ariane Rüttler. So these are properties we need if we want to formalize and model, for example, class diagrams. In class diagrams, we have references. References are usually or can be understood as set-valued maps, as set-valued functions. We call them multimap short. So we have multiplicity constraints. The arity is just, this is a property of an arrow. Surjectivity is a property of an arrow. Inverse, so means that we have two references that carry the same. I think the technical term is opposite references. So they carry the same information, only that they go in different directions. Here we have, again, the composition property. Then we have something that we call image inclusion. So for each element here in a set A, f of A is contained in G of A. This somehow turned out to be necessary to model things. And there are a lot more, but I haven't put them here in these slides. So what is now a sketch? A sketch is now, so in analogy to Ehresmann sketches, we don't have now a graph here, but we have a object in our base category. And then we have a set of atomic statements. And atomic statements. And what is an atomic statement? So we say what kind of statement it is. Here's the name of the feature symbol, and here's just information where we put this statement, what part of our graph K should, for what part of our object K the statement should hold. So delta is morphism in base from the arity of f into k. So this have been the diagrams, cones and co-cones in Ehresmann sketches. And here's a very, very simple thing. So we have these double triangles. So we have two arrows down here, and we declare both arrows as a composition of xe1 and xe2. Yeah, it's stupid, but that's just what we do. So we declare as well xe3 and xe4 as a composition of these two arrows. And this we can do because we have predicates and not operations. So, and this is the other example from class diagram. So we have three classes: employee, project, department. We have an association between employee and department model as a pair of opposite references. We have some multiplicity constraints. So each employee has to work in at least one department, and the other way around. Yeah, this comes later here. In other, the other way around, it's a good, no, I just forget it. Then we have project, and each project is controlled by one or more departments. Then we have the information what employees are employed in a project or work in a project. And then we need to compose these two arrows here, these two references, to get this arrow that tells us about all employees that are working in any of the departments that is controlling a project. Yeah, and the requirement here is, the design requirement is that any employee that is working in a project should be an employee of one of the departments that control the project. Yeah, we cannot just have people from outside working in the project. Questions?
Yes, I'm sorry, I don't get the relationship between this picture and the previous framework. So what's the base here, and what's the?
Good. So I don't show, I mean, if you forget about all these, if you only take these here, that's a graph. That's a graph, yeah, with three nodes, 1, 2, 3, 4, 5 arrows.
Okay.
And now I have it here. Here are the constraints. Yeah, here are the atomic statements. Yeah, we have a delta, so we put a constraint, this multiplicity constraint, on this arrow.
Okay.
We say that the arrow in the other direction, this one here, that this is surjective. Then we say also that this arrow here has this multiplicity. So formally, this is a graph homomorphism from this arity into this big graph. And usually we visualize those homomorphisms in this way. Yeah. So this arrow in the graph should have this property. It should have this multiplicity property. Yeah. Is this answering your question?
Yeah, I think so. So in that case, we're still living in graphs. There's no change of.
No, this is just not to go too far away. It's just to,
yeah. No. Okay, I just to make sure, because.
No, okay, I understand. The point is, I don't want it to go. I want kind of to reconstruct Ehresmann sketches within generalized sketches. Yeah, so not to go far away and drawing complicated diagrams. So therefore, I have chosen this example. So in the background is somehow the idea, okay, we have Ehresmann sketches, and now we try to reformulate them within this more general framework.
Okay.
Yeah. So examples, a little bit more advanced examples I will have in the other talk. So at least some typed graphs and things like this.
Maybe could you just give an example of a base category that is not graph, just to get some information about what the kind of generalization is that you're looking at?
Usually typed graphs. That's the best example. But I don't have a slide here now.
Mm-hmm.
Yeah, we can have type graph, we can have e-graphs. So in my lectures in my category theory course, I'm drawing some e-graphs. And yeah, so these are the examples we usually
Graph potentially with more annotations and more sort of structure on them. Okay.
Okay, I get it. Thanks.
Yeah, especially in software engineering, it will be typed graphs. Yeah, so it will be typed graphs. So yeah, maybe I should.
Okay.
But as I said, in general, you can take any category you want. So it's of course so. And good. So now we have somehow to if you go back to Ehresmann Sketches, so here we have a graph. So this is our K, and then we have these three properties here, and we have somehow to say what we take instead of this category theory, where we interpret this graph G, and what we take instead of the concept commutative diagrammed limit cone or co-cone. So we have somehow to tell or to know or to define. Yeah, we want to reconstruct this concept of a model, and we have to give it a name. So we choose a structure. In the case of Ehresmann Sketches, we choose a category, and here we have a structure. A structure U is given by an object in base, the carrier of the structure, and then we have to for each feature, for each predicate symbol, to tell what are the valid interpretations of these feature symbols in F. So this will be a subset of all the morphisms from the arity of F into the structure. Yeah. In case of Ehresmann Sketches, this would we have a definition behind, and we know what are the limit cones. We don't know, but at least we can define what are limit cones, what are co-limit cones, what are commutative diagrams. So in category theory, we know what this should be. And here, because we allow here arbitrary features, we have just to say it somehow. What are the valid interpretations of these feature symbols in A? So, and in Ehresmann Sketches, we had graph homomorphism from the underlying graph G of the Ehresmann sketch into a category C. And correspondingly, we have now morphisms from K to U, and we may call them just interpretation of a context in a structure U. And now we have a concept of a model. A model of a theta sketch K is an interpretation of the context K, the underlying carrier of the sketch, such that this interpretation satisfies all the atomic statement in K. And what does it mean? This means, so here I have now my sketch. Yeah, here I have a constraint in my sketch. Here I have the interpretation of the underlying object of the sketch K into the carrier of my structure U, and I just compose them, and then I check if this is a valid interpretation of F in my structure. Yeah, very easy, very easy. So, but this is exactly the same pattern as we had in Ehresmann Sketches. Questions?
So just to make sure I understand that. So that means the structure replaces the target category.
Yes.
And the Well, model is obviously the interpretation is a functor, and the model is a functor that preserves.
There's no functor. There are just morphisms in the category base.
If I translate back, then the model would be a functor that.
There was no functor, Reiko. There was only graphomorphisms.
Yeah.
Yeah, because a sketch is a graph.
Yeah. Okay.
These are graphomorphisms. Everything.
Okay, so then the model is a graphomorphism. In Ehresmann, the model would be a graphomorphism that maps the designated sort of cones and cocones to.
Yeah, there was this. Should I go back? I don't remember. There was this phrase: transforms a cone in the sketch into a limit cone. Yeah. So this is a cone in the sketch. Composed with this gives you a limit cone in your category. Yeah. And this phrase gives you a limit cone. This is now replaced by this set of valid interpretation. Yeah.
Thank you.
So, and of course, we somehow touched upon this already. The properties commutativity, limit, and co-limit do have a fixed axiomatization that we can universally apply for any categories. And the question is now how to describe arbitrary user-defined properties. And the observation is if you look at the structure of the universal properties of limits and co-limits, they have a very simple logical structure that are expressible by something we may call sketch implication. And the sketch implication is just, I mean, this is in analogy to conditional equations in algebra or to Horn clauses. In logic, the sketch implication has, so we have two sketches, the premise sketch and the conclusion, and just a morphism between the carriers, the underlying objects of these two sketches. And the idea is, since co-limits and limits are kind of very expressive, are good enough to specify limits, it may be also good enough to specify the things we need in software engineering or in other things. So that's the first trial to specify the things. And here's a very simple thing. Yeah, here we had this sketch where we declare that these two arrows are at the same time the composition of these two other arrows, and we just force them to be equal. Yeah, if there are two arrows that are declared to be the composition of two given arrows, then these two arrows have to be the same. Now this is just this sketch implication. So concerning limits and co-limits, the corresponding uniqueness of mediating morphism would have this kind of structure. And we can also make existence of things. We can say, okay, whenever I have two successive arrows, then there should be a third arrow that is a composition of these two arrows. Yeah, so now we somehow define the properties of composition, and we can do correspondingly for identities.
So Uwe, this is a bit like giving
What?
a specification commutative diagram calculus. No? It's a bit like the two conventions one might take for commutative diagrams. It's actually quite interesting.
Yeah. So, okay, this I have. Yeah, this was a definition, and now we have just to say what it means that structure satisfies a sketch implication or the sketch implication is valid in a structure. And this means that any solution of the premise can be transferred into a solution of the conclusion. Yeah, whenever I have a morphism, iota, where is it now? Iota from P to U, such that so that this structure or this interpretation satisfies all the statements, all the constraint in the premise sketch, then I can extend iota to rho. This means that I get a commutative diagram here, such that rho satisfies all the requirements, all the constraints in C. Yeah, so that's the usual thing. And yeah, and this can be used to axiomatize semantics of feature symbols. Yeah, so like here, so we have just this. Yeah, any category would satisfy these two implications. Good. This is my approach coming from algebra and coming from Ehresmann sketches. There are models. Yeah, there are models in the classical sense of first order logic or of algebra and algebra of universal algebra. And then you look at Makkai and we get a kind of surprise. Makkai doesn't consider structures, interpretations, and models at all. So he only works with sketches. But as I told, this all are my interpretation. So he relies on a trick that we may call syntactification of structures. Yeah, so in the area where I come from, algebraic specification, we use this trick to construct initial and free algebras, and especially also free functor semantics of parameterized specifications. And the idea is very, very simple. Let's say we have the natural numbers with the addition operation, and then we just represent the structure by choosing, say, okay, we have the natural number. We may call it, I will usually call it now a context. And then we just write all these equations. 0 plus 2 equals 2, 3 plus 4 equals 7. Either we take only these basic equations that somehow represents the graph of the plus operation, or you take arbitrary terms with n terms with n elements from n on the leaves, and say, okay, this is a representation, and then you translate this representation and make other constructions. And this is what he does. So this we can do the same trick on this very abstract thing. So we have a structure, and we can transform a structure into a sketch with the same underlying object, with the same carrier, with this underlying object of the sketch as the carrier of the structure. Then we just translate all this knowledge. What are the valid interpretations of feature symbols in our universe? We just replace it by syntactic statement, syntactic, yeah. And why it's now syntactic? I mean, in case of algebras, it's clear somehow that term and expression is syntax, but on this abstract level, it's so at least F is a symbol, F is pure syntax. And usually what we can think about if we write things like this, that this delta here is rather taken as a syntactic representation of this morphism we have here, of this morphism from alpha F to U, that is an element of this set of valid interpretations of the feature F. Yeah. But if you go so abstract, then the distinction between syntax and semantics is rather blurry. The interesting point is now, the real interesting point is that the validity of a sketch implication in a structure turns into a closedness property of the sketch. Yeah. So now I have this implication. And what does it mean that a sketch K is closed with respect to this implication? This means if I have a match iota here of P and K, then I can translate all the all the statements in P into statements over K. Yeah, I can just compose this statement here with iota, and I get a statement in K. So if all the statements in P translate into a statement in K on the nose, then I can extend J to a morphism phi such that this commutes here, such that all the statements in C can be translated and exist on the translation of all the statements in C exist in K. Yeah. And that's a fact. Then, so the structure satisfies the implication if and only if the sketch, the syntactification of U is close with respect to this implication taken as a kind of rule, yeah, syntactic rule, deduction rule, if you want. And I don't know if you have ever made this kind of completeness proofs or. So this kind of closeness characterization of syntactification is the main ingredients of completeness proofs. And in case of generalized sketches, we apply sketch implications as deduction rules by constructing pushouts of sketches until we obtain a closed set of atomic statements. And once you reach the closed set of atomic statements, you are somehow finished, you translate it back into a structure, and this is then the corresponding initial algebra or free algebra or whatever you want. Yeah, and this usually proves, gives you completeness proofs that you are able to, that you have a syntactic procedure, a deduction calculus that generates you syntactic representations of structures. That's the whole key observation, how completeness proofs are done. And Makkai presented it here for sketches and sketch implications. Good. So now we are a bit, how much have 5 minutes or?
Yeah, something like 5 minutes, maximal 10. Then we just meeting.
Yeah. So, okay. So Makkai, no structures, no models, only sketches, only sketch implications. And to be able to stay within this pure setting, he works with a hierarchy of sketches based on a construction one may call internalization of atomic statements. And this, to have this internalization, we should rather restrict to pre-shift topos. And yeah, Zenobi tried to explain me this 17 years ago, but I was pretty ignorant in the beginning, but then I got it. So that's a very simple example. Again, we start with graphs because it's so nice and easy. Now we take two properties, monic and final. So monic is a property of an arrow, and final is just says that an object is a final object. And what we do, we internalize now these. We internalize these features. We add these features to this meta model of graphs. Now we have a new arrow mon, a new arrow final, and then we draw arrows corresponding to the signature. So here we have one arrows. The arity of mon is given by one edge and two nodes. So we have one edge and two nodes, and that xv1 is a source of xe is encoded by this composition. The composition of this xe with s gives us xv1, and the composition of xe with t gives us xv2. So that's the encoding of the arity of this feature. The same with final, but final has only is a property, so we have only one arrow. It's a property of a node, so we have only one arrow from final to xv. And and now any theta sketch can be represented by a functor from this extended meta model into set. Yeah, graph was an interpretation of this meta model in set. Now we extend it, and a sketch is now nothing. Or if I have a sketch, then this sketch can be described or translated into a functor from this extended model into set. And the whole idea is that this is somehow what you do if you create an association class in object-oriented modeling. So these token here, these elements here are just holding a constraint, and what constraint is affected by this, what parts of the model are affected by this is just given by this map, and you have just to follow these maps here to find out which elements here and which elements here are affected by this constraint. The other way around, if I start with the with the functor here, we may have a problem that two tokens describes the same constraints, the same statement. Therefore, we have to go to multi-sketches. We have to go from sketches to multi-sketches. And a multi-sketch is just, so there a statement, it's not enough to know the name of the property and the delta. We also need to have an extra identity. So each atomic statement in a multi-sketch has its own identity, independent of the property and of the delta. And then we can consider the category of theta sketches, of all multi-sketches and theta sketches with sketch implications as arrows. And by this construction, where I gave only an example now, we have these isomorphism of categories. Yeah, all the theta meter sketches for this base category, for these topos, pre-shift topos as base category, this category is isomorphic to this pre-shift topos. Yeah, so we internalize somehow all these symbols here. They become now part of the meta model, and we get this isomorphism between categories. And just to remind you how you could start with a very simple, could start with set. So, and yeah, describe set in this way. It's just we have here the terminal category with exactly one object. Then we choose alpha. So we have one symbol R for relation. Then we take as arity, we take just a set given by two elements, X and Y. And a statement on a set is just a map from these two elements into the set K. And this can be described, and the statements are just then given by the name R and a pair representing these images of X and Y with respect to delta. It's just a pair of values in K. So you have these equivalents, we have these isomorphism here. And the quiz is now, what is a multi-sketch? I will answer it. It's just a multigraph. Yeah, and what I construct here by this construction is just another variant of the meta model of directed multigraphs. Yeah, so good. And the point is now we can iterate. Yeah, so we start with a meta model. We start with the category B0. We define and given category Bn. We choose a signature with the corresponding topos, pre-shift topos as base category. Define this arity map and construct this next category. Yeah, this needs level. So, and the observation is if B0 is a finite discrete category, and all these sets phi n are finite, then all the categories Bn are simple categories in the sense of the false paper, that I showed you in the beginning. And these simple categories are exactly what people in homotopy type theory think it's the best thing to work with these, what they want to do with these, have control of these equality types. And just to mention, so my colleague, he started a software project, MIOT, make your own type theory to program these things. So he makes these extensions. So that's like defining a recursive data type in a functional languages, so something similar, and then you just get more types and more operations for your in your formal system. Good. This is only where we start. So what one can do now is not to start with sets of feature symbols, but with categories. So this is what I have been done 17 years ago. Everything generalizes, and then one can ask, okay, if I have it now on this level, what is the inverse of this construction of this internalization? And this is actually the generalized GReTA embedding. I don't know if this is the right name. So you start with the category C, then you take two subcategories, A and B of C. And then you have this thing. You first choose an object in A. So then you get, and for each object in A, you get a corresponding functor from B to Z. And if you vary all the objects in B, you get these functor from A up into these topos here, into these pre-sheaf topos. Yeah, and if you look at this directly, then you say, okay, what we do if we start here with C, these meta model that we construct by this internalization. E represents the category of feature symbols, and B is B. Then you the generalized GReTA embedding reconstructs this arity functor. So in other words, what you do here, you take C, you make a cut and say, okay, one side is syntax, the other side is semantics, and what you get is a generalized sketch. Yeah, and the question is, if I do these constructions, if I start in this way, I take C and I take two subcategories of C, when do I get an isomorphism like this? And the answer is, okay, if A and B are disjoint, non-empty full subcategories of C, where that is a partition of the objects of C, and where there is no arrow from B to A, but only arrows from A to B. Then this construction, so GReTA, generalized GReTA embedding on one side and this internalization construction on the other side, they are inverse to each other. Good. Last slide. Zinovi mentioned pro-functors already 70 years ago, but I never had time, courage, and mental power to have a closer look at this. But at least it's true that pro-functors are very much related to generalized sketches, even if I never understood it how. And I had a colleague in Romania, she told me once, I asked her about it, and she said, okay, this we know. And she said these constructions, this internalization construction is just something that we call collage or co-graph of a pro-functor. So I just wanted to mention it. Good. This is not necessary now. Thank you for your attention. Good.
Sorry, I just wanted to say, unfortunately, I now have to switch over to the other Zoom meeting. We'll of course stay whoever wants, and there will be the second part of the talk, and afterwards we have time to discuss. So it's a little bit unusual.
Yeah.
I apologize. Uwe, could you also switch over to the other meeting, please? So, and everyone.
Yes, I have to stop sharing and get out and get the other one. Yes, good.
everyone who's on the call, you need to take the registration for the other Zoom meeting if you haven't done so, or use the actual links to the other one. So we'll be back in 1 minute or so. Thank you.